Hello guys, welcome back. And in this session, I'm just gonna talk about a crash or embedded Rust code crashes right after uh, executing underscore start in the RISC-V board. And we would see what causes the crash, and we would also see how to fix that when you run embedded Rust code. Okay, so for people who are uh, not aware of the difference between an embedded Rust or running embedded Rust on an hardware where there is no operating system, whereas versus on a platform which has an operating system. So this table just highlights minimal or very few differences, but these are very critical differences. So first one, on a hardware which does not have any operating system, in when you run embedded Rust, so the entry point should be underscore start. Whereas if that has an operating system, then the entry point for the Rust is main. And when there is no operating system, then the standard library wouldn't have been ported, and any memory management utility like malloc and okay, in Rust you don't have malloc. Any standard library functionality which might use a memory management, not even the standard library would be ported, and it wouldn't be available on a platform if there is no operating system. Whereas if the operating system, for example, if Linux, if you have a hardware on which Linux is running on a RISC-V platform, then it's easy to bring up Rust because the standard library would be already available. Uh, so our major focus is, as you know, that I have been trying to bring up embedded Rust, develop embedded Rust code on RISC-V based hifive1 revision 1B board. I I briefly observed this before, but I'm gonna discuss about that elaborately in this session. So why the crash happens and how I have fixed, and my uh, fix is may not be generic. It's just what I thought, or it's my own way of fixing it. So on an platform when there is no operating system, so right after compilation, so the entry point would be underscore start, and then there is no standard library. So what happens to the stack pointer? Okay, this was the um, major question. So if you are from a if you have ported operating system or any C library on top of a hardware from bare metal, so what you would do is, like, very first, there would be some certain code in assembly where you would set stack pointer and few other registers, and then you would jump into the C library. So we would see why that is important, and that same is applicable for Rust as well. Okay. So now when I boot from Flash, I haven't observed this before when I executed the code from RAM, but however, when you boot from Flash in hifive1 revision 1B board, so this is a boot sequence, and whatever is highlighted in green is fixed at the manufacturing of the chip itself, and we have no liberty to modify any of this. So the scope of changes is only after the execution jumps into the flash. Okay, so these are all like one-time programmable memory and MROM and ROM. These are all fused during the manufacturing of the SoC. And if you refer the FE310 manual, then right after this, the execution would jump into the start address of the QSPI address. So if your code, or when you build and link Rust code, and if your underscore start is pinned to this location, then there's a very good chance that the stack pointer might be initialized, or it might even have a stale value, or it might, right after reset, it points to an invalid memory. That's why uh, when it jumps into this location, the stack pointer is accessed, the crash happens. Okay, we will see more about this. So first, I would like to go through the changes I have made in this regard, and then I would discuss why that is made and what would happen if you don't have those changes. Okay, so if you see here, and this is the if you go to the development branch of the Rust on RISC-V repo, and 2 days ago you should be able to see a commit which is 2 days older, and let's go to the commit. So this one is to prevent compressed instructions for now. Okay, so what this change would do is, okay, let me go back to the slide. So I'm sure that you would have been aware of the architecture flags that you would be passing to the compiler. For example, when you compile a C code, you would pass a flag like mark, followed by whatever the uh, architectural or the orc related flags that you want to set to the compiler. So for example, if you go to the RISC-V code, and if you observe the build script, you see here, this is an MR-RV32IMEA. So since the arc flag has been set as IMEA, all the instructions would be 32-bit wide, since there is no C here, which stands for the compressed instruction extension of RISC-V. Since I did not add the C flag, though the hardware FE310 supports compressed instruction, since I have not enabled in the mark, all the instructions that have been generated by the compiler would be 32 bits wide. So now directly when you pass this to the assembler and compiler, this is how we do. However, when you pass the flag through cargo, and you know that cargo has the so in the cargo config file, you pass the flags for the rustc or the Rust compiler. And if you want to know what are all the target that is supported by the RISC-V 32IMAC unknown non-ELF toolchain, then you can just find that out using this command. At the same time, for each target, if you want to know what are all the target features, then you can get the list using this command. And in my case, where I want to eliminate those or prevent compiler from generating the compressed instruction. So what would happen if we allow compiler to generate the compressed instruction? So not all RISC-V instructions has a compressed instruction set. What I mean by that is like when you enable the support for compressed instructions, then few instructions would be 16 bits wide and few would be 32-bit wide, and that would cause misalignment in address, because instructions can be 4 bytes or 2 bytes. Then of course any address can be 2-byte aligned instead of 4 bytes aligned, and at this stage I do not want that to happen. That's why I have prevented the compiler from generating those compressed instructions. And the same flag if I have to pass it to the Rust compiler in Cargo, and this is how I do, and I learned about this from the Rust forum. You can see the link below for that. Okay, and that's what I would have done here. If you go to the Rust and config, okay, so I have just passed this -c flag. That means that remove the feature of compressed instructions. Okay, and now if I cargo clean and compile, go clean and cargo build, and let's, if you see all these instructions, those are generated would be now 4 bytes. Okay, so it'll be 4-byte aligned, and this wouldn't cause any address misalignment. Okay, so that's the one which is one of the recent change which I have submitted. Let's go back to the, and that's one of the commit or prevent compressed instructions for now. And the next commit which I would talk elaborately is the add pre-state blob to fix stack pointer. And this one, so if you see, this is a change, and let's go to the code, VS Code, and it will be very clear here. So if you go to the, I think I did not make the change for the print binary. However, I just made the change for the LED blink uh, binary. And as you know that the repo rust on RISC-V, I have 2 binaries in it, and I have made the fix only for LED blink. So this is the entry point for Rust, embedded Rust. So so what I did before is I just compiled and linked to the start address of RAM to this underscore start function, and basically if you go back to this, so the underscore start would be at the right of the, or would be at the very first instruction of the start of the flash memory. Okay, so what that had caused is, if you go to the underscore start function at the very first, so this is the underscore start, and when Rust compiles, the very first line is it decrements the stack pointer by 32. So I'm not yet thorough on the uh, binary interface for Rust on RISC-V. However, I see from the code that right at the start, uh, the embedded Rust expects that the stack pointer has been already set, so it just decrements this by X bytes based on the local variables in start, and it start using it. So the crash happens because of this, because right after the reset, if the stack pointer, for example, if I run some code before from the through using GDB, and when the stack pointer points to some valid address, and then if I load this code and run, then underscore start, then you would see this code working well, because any valid address, it would just decrement and push these variables, and then it would keep using it, all good. But what happens after, once you flash this code into the ROM memory or the flash memory, and then if you just create a power cycle with a uh, power button, then what would happen is it would just follow this sequence, and I see that right when the execution jumps into the start of the flash memory, the stack pointer don't point to a valid address and it keeps crashing. Okay, crashing in the sense like you would see some exception. Okay, so how to prevent that is instead of uh, linking the underscore start entry point to the very start of the address, what I have done is if you go to the linker script, long ROM linker script, so as you see that I have committed few changes regarding to linker as well. So in the ROM linker, uh, so at the very first, I have asked the linker script to keep the pre-start section, and in the LED blink, the pre-start section is this, and all it does is set the stack pointer to, excuse me, to this address, and then it jumps to this address in the flash. And this one is straightforward, that you have to set the stack pointer to a valid RAM address, and I have given 4 kilobytes of stack size. If I set it to, because the RAM address starts from 8 followed by 7 zeros hex value, so this would be at least 4 kilobytes. Okay, that's why I stack 4 RAM address. However, the flash jump address, how did I arrive as? So I have added this pre-start blob. Then if you see if you dump the objects in the file, you can see that this is a pre-start code. And if I keep closer to each other, so the NOP, and then it sets the stack pointer, and then it jumps into the 2008. What is there in 2008 is the start. So this, by this way, when the execution jumps into the start, the stack pointer has been already set. Okay, so I know that this is so the way of fixing the jump address with the fixed value will work only for this code. But there are several ways that you can find. Either you can pin this to a particular location, and you can always pin this start address to a particular location in linker and then jump to that. There are several ways. This is just one of the way, and I just want to demonstrate that you can fix it so that every time I run the code, it would work properly from the flash, for example. So let's get into the let's see the board now. So let me connect to the board first. So if you see here, I connect through OpenOCD with a flash underscore openocd.config. That is another config file which I have committed into this Rust repo. And once the OpenOCD is, now it's waiting for a GDB connection. So let's build now. Okay, so it's just LED blink code. Remember this would you can see on the right side. So this load would program the code into the flash memory. through OpenOCD because OpenOCD has already support for the SPI flash in the board. Once it's loaded, now if you just continue, you can see the LED blinking on the screen. And let me cancel that. And the most important thing to validate is the moment you, now I will just cancel the, and if I unplug and plug in, then still the code should be there and the flash, and it should be able to boot again from the flash and the LED should be blinking. Okay, so let's make some change here, like let's increase the delay. So now the new code is programmed with a different delay into the flash. Now let's see if the, yeah, now you can clearly see the difference between the first on and off duration of the LED and the one now. So what I'm going to do is now, since it's programmed, I would cancel. So what difference has this setting the flash has made is that before, even before, if you connect with GDB and if you can set the stack pointer to some valid address, and then if you program and it would work. But what would happen if you just unplug and put the board through a power cycle, would that it would just cause an exception and the LED will not blink. Whereas now with this pre-start, it's guaranteed that the stack pointer is always set. So now all I can do is just go ahead and get out of the OpenOCD and GDB, and I can just unplug and power cycle this till you should be able to see the LED blinking, but with a longer delay or longer on and off time. Okay, so that's all. So if you are interested more on this kind of videos, please feel to like, comment, and if you also have any questions in this regard, please post that in the comment section. At the same time, do go to the repo and get a chance to download this code. And also this video is applicable for both of my channels. As you all know, I have one channel for RISC-V and other channel for embedded Rust on RISC-V. This fits into both, so I will load the same video on both the channels. Okay, yeah, thank you, and see you in the next session.